Hello everyone, this is the third video of chapter 2 of the lecture notes, Fundamentals of Cryptography. In the previous video, we introduced a very important distinction between what we call symmetric cryptosystems and what we call public key cryptosystems. And I told you that public key cryptosystems are very important in the way we think of cryptography in modern day. So we're going to spend the most of the lectures discussing this type of cryptosystems. However, in this video, we're going to focus on symmetric cryptosystems, and we're going to explore a few concrete examples of how this works. I'm sharing with you an image of the lecture notes so that you see which section of the lecture notes we're covering right now. So it's section 2.2, and I really encourage you to read them because the content is described there in more detail, and the examples in the lecture notes are different from the examples I will give you here in the video. So really the material complements each other, and if you want to understand very well what the content of this section, the best is to use both the videos and the lecture notes. Okay, so we have already seen one example of a symmetric crypto system. Is the same example that I have been giving in the last two videos, is what I call the shift crypto system, which, as we saw, associates letter A to letter D, letter B to letter E, letter C to letter F, right? And so on. It continues with alphabetical order. If you want to make this a little bit more precise from a mathematical point of view, we need to associate mathematical objects to the letters we are using. And the most natural thing to do is to just associate numbers, right? So associate to letter A, since it's the first letter of the alphabet, number 0, to letter B, that is the second one, and so on, right? C is 3 is 2, and then we continue with D here, that is 3, E, that is 4, and F, that is 5, okay? So if you think, what is the mathematical transformation that we are using here when we have as an input a number and as an output a number, you see that the only thing that we're doing is adding +3 each time. So you would say this is the mathematical transformation we're using. However, you need to be a little bit more careful than that, because if you think what happens when we're using the last numbers of the alphabet, actually, it doesn't work exactly in the same way. So Z is the last letter of the alphabet, and there are 26 letters in the English alphabet. This is therefore number 25. This is number 24. And X is number 23, right? And in this shift encryption system, X gets transformed into A, which is 0, B is 1, and C is 2. So you see here that the simply adding +3 doesn't exactly work. However, just by remarking that 0 is the same as 26 modulo 26, right? That 1 is the same as 27 modulo 26, and that 2 is the same as 28 modulo 26, you see that the idea of adding +3 works only if you put this idea that we are working modulo 26, in fact. So just put bars here everywhere to insist on the fact that we do not work with integers, but we work with numbers modulo 26, and now you have the good transformation, okay? So let us write it here. In this shift transformation, we have as an input a number on Z over 26Z, as an output another number modulo 26, and the transformation is that it takes as an input X, and it gives as an input X +3, right? So that's the enciphering transformation of this system, okay? So I have called this system the shift transformation, but it's most commonly called Caesar's cipher. Caesar's cipher, following the name of Julius Caesar, the Roman emperor, who apparently used this system to cipher some of his diaries during the Roman wars. Okay, so this is the first example of a symmetric crypto system, right? And we can take this very simple system and we can generalize it in two different directions. So we're going to use this example. Sorry, I have to, I have a small problem with my notes, so let me just open it again and share it with you very quickly. Sometimes it happens. Okay, Caesar cipher. Okay, here it is. And we can generalize this in two different ways, as I was telling you. The first way in which we can generalize this here. Okay, so two different ways in which we can generalize. The first way in which we can generalize Caesar cipher is instead of taking each letter of the text and transforming it, we can work with p-grams. Okay, so take p-grams, blocks of p letters, take p-grams instead of letters. Of letters. And working exactly the same way. This means that instead of working with just one letter, you work with a vector in which you have p letters, right? x1 to xp. And when you cipher this, or you just take this vector and you add to this vector x1, xp, you add a common constant vector, right? p1 to bp. Okay, so I should put bars everywhere to insist on the fact that we're still working modulo 26 or modulo whatever number of letters we have. Okay, so this idea is very simple, and this is called, in fact, the cipher of Wigner's cipher, which was used until the end of the 19th century by the military in Europe. Okay, that's the first way in which we can generalize Caesar cipher. The second way in which we can generalize it is that instead of using the simple transformation that we're using, x gets transformed into x plus 3, well, you can allow the number here, the coefficient in front of the x, to be different from 1, right? So you can say, for example, 4x plus 3. This makes a new transformation, which is a little bit more complicated. Okay, so here, second way of generalizing, take affine transformations instead of just shifts, right? Instead of shifts. Okay, so this still goes from z over 26z, let's say, if we're keeping the same, and gives another number in the same 26z. Okay, and then we can, of course, combine the two ideas into and get a more sophisticated system. That is the one we are going to discuss a little bit more in detail. So if we combine the two ideas together, we get something that we call the affine cryptosystems. Affine cryptosystems on p-grams. Okay, so let us spend some time discussing this sort of symmetric cryptosystems in some more detail. The first thing that is important is to recall the definition of what is an affine transformation. Okay, so an affine transformation here, let's recall precisely the definition of what it is. So it's a map, and it takes as an input some vector which has the coefficients in z over nz, and it has, let's say, p components, the vector. Okay, so we have some vector here, x1 to xp, and these are all numbers modulo n. As an input, the output here is z over nz modulo p as well, so it's another vector. Okay, input and output are both vectors. So here we have y1 to yp, and this vector is simply found by taking some matrix A multiplied by the vector x1 xp and adding to this a constant vector b, b1 to bp. So that's an affine transformation. Okay, so let's call this affine transformation F, and it depends on the choice of the matrix A and on the choice of the constant vector b. Okay, so let me just insist here, maybe write it down. A here is a matrix, n by n square matrix, right? Okay, so that's an affine transformation. And the idea of affine cryptosystems is that we're going to use as enciphering transformation an affine transformation. However, we just need to be a little bit careful because not all affine transformations can be used as enciphering transformations. there is one condition that has to be met, is that an enciphering transformations needs to be such that it can be deciphered, right? So therefore, it has to be a bijection. You have to be able to go in one direction, and then you have to be able to go in the reverse direction. And not all affine transformations are bijections. So let me just write you here the condition that affine transformations need to meet so that they are bijections. FAB is a bijection if and only if, and this will not come as a surprise, the matrix A is invertible, right? And then again, the matrix A is invertible if and only if the determinant of A, and here you need to be a little bit careful because we're working modulo n, is relatively prime with n, okay? So really be careful here, because you can have, if you're working, let's say, modulo 10, and you have the determinant of the matrix to be 5. 5 is not relatively prime to 10, so a matrix with determinant 5 is not invertible if we're working modulo 10, okay? So the normal condition that you are used to work with real numbers or with complex numbers, that determinant is different from 0, does not work here, okay? The important is that the determinant has to be relatively prime to the modulus you're working with. Okay, so now that we have this, what is an affine transformation and which are the allowed affine transformations that we can use when doing encryption, we can just tell you what is the affine cryptosystems and pgrams. Affine cryptosystems and pgrams. On pgrams. Okay, so as I told you at the beginning of the last video, when you're defining a crypto system, you need to tell me two things. The first thing is which are the message units that you're taking. So of course here, message units, well, as the name says, it's the pgrams, right? So blocks of p layers, okay? And in the second thing that you tell me is the enciphering transformation, right? Enciphering. To encipher, so you're going to take some transformation that we're going to call enc, right? It takes as an input z over nz p, so a vector here, right? As an output, another vector z over nz p, so the vector is p rows here, and let's call x the input, the output is y, and as we said before, y is just equal to A, the matrix, times x plus some constant vector b, right? So we put as a label here of the transformation the A and the B, okay? Here, where A is an invertible matrix, Okay, so that's the enciphering transformation, and this A and B here are the enciphering key. Okay, and since this is a symmetric crypto system, normally the only data of the enciphering transformation is enough to know how to decipher a message. So I shouldn't even tell you how to decipher a message here. I am just going to write it down to convince you that this is a symmetric crypto system. So how do you do this deciphering transformation? It works in the opposite direction. So deciphering takes as an input a vector, because we're just dealing with vectors all the time, right? The input and the output are both vectors here, z over nz p. And instead of taking the plain message as the input, it takes the ciphered message as an input, y, and it's going to give as an output here x. And x, how do we find it? Well, just read this equation here and isolate x in this equation. So this is very simple, it's a minus 1 y minus a minus 1 b, okay? So that's how it works. And therefore you see that in the deciphering, both parameters that will is a minus 1 and minus a minus 1 times b. So this is the deciphering key here. Okay, so let us just finish this video with a concrete example of how to cipher a message using this affine crypto system, which should not be a problem because it's quite simple. It's just using linear algebra that you are used to work since at least 2 years ago. Okay, so let's look at this example. I want to work with you. So we're going to work with trigrams. Let's use message units are the trigrams. Okay, so blocks of 3 letters. And I'm telling you that the ciphering key, okay, and ciphering key is going to be the following matrix A. So where is it? I put it somewhere here. So 1, 2, 1, 0, 3, 5, 0, 0, 7. That's the matrix A. And I'm going to make it very simple and just choose for B the 0 vector. Okay, and to make calculations a bit simpler, one thing that I haven't mentioned here is that we're going to use an alphabet of only 10 symbols. Use an alphabet. So we will be working with n equal 10. An alphabet of n equals 10 letters, right? And the 10 letters that we'll be using will be the first 9 letters of the alphabet: A, B, C, D, E, F, G, H, I, and the blank space so that I can work, make different words. Okay, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, now with this information, we're going to cipher the following text. Cipher the following text, which is, I tried to find a text which made some sense only using these words, these letters. So acceded space, blank space, beach, ahead. So that's the message we want to cipher. Okay, so how does it work? The first thing that we have to do is decompose this message into trigrams, right? So first trigram is ACC, then we have EDE as the second trigram, third one D blank space B, then it's EAC, then it's H blank space A, HEA, and the last one, since D is alone, we're going to suppose that D comes with 2 blank spaces at the end. Okay, so it becomes a trigram. Okay, so now how do we cipher this? Let's start with the first one, ACC. So ACC, we're going to think of this as a vector, right? ACC is the vector, okay, here, which corresponds to the, in letters, corresponds to 0 to 2. 0 to 2, right? Now we're going to cipher this. This is the, so far we have done nothing. Now we're going to cipher this by acting on this with the matrix A. A 0 to 2. Okay, so we just made the computation. This means that we're doing twice the second row, twice the second column, plus twice the third column, and therefore it becomes 6, 6, 4. Okay, remember that we're working modulo 10, right? So for example, 2 times 7 is 14, but modulo 10 is only 4. Okay, so this is 6, 6, 4, which corresponds in letters to, so we have the table here, the correspondence table here, J, J, and 4 is E. Okay, so that's how it works with the first one. Let's just make one more, and then I'll leave the rest for you to work it out. E, D, E, which corresponds in terms of letters to 4, 3, 4, 3, 4, and then we apply the matrix A on this, A, 4, 3, 4, and if you use matrix multiplication, the used common matrix multiplication, and just work modulo 10, the result here, I wrote it down somewhere, so I'm just going to tell you the result is 498, 98, and this corresponds using the table. Here, 4 is E, E, 9 is blank space, and 8 is I, right? I here. Okay, and this is how you should work with all of them. So I'm just going to give you the final result, and I'll leave it for you as an exercise to check that this is indeed the case, that this is the ciphered message that you get. So you get GG, E, blank space, I, C, C, H, H, F, B, F, H, A, F, C, A, C, D. So that's the final message that you get from the plaintext acceded bit ahead. Okay, so I leave it as an exercise for you, and with this we complete the material of chapter 2. There will be one more video with explaining or solving one concrete exercise with you, and we'll now move on afterwards to public key cryptography.